Okay, continuing this conversation about multiple bonds. When we use valence bond theory to look at covalent bonding and multiple bonds, then we start to understand why we don't see any kind of bond rotation around multiple bonds. So if you have a single bonded, two elements bonded together by a single bond, they'll rotate around that bond a lot. Constantly. It's one of their forms of like kinetic motion. But the second you put in a double or a triple bond, it can't rotate anymore. And that's because when we create these overlapping pi bonds, they're coming at each other, right? Parallel and perpendicular to the axis of the bond. If you rotate them, they're going to split. And so rotating would require breaking our pi bonds, which would show, it's shown right here. So you see how if we rotate along that sigma bond that's connecting the two carbons, then what we'll have is these pi bonds break, and that's breaking a bond. We've talked about bond energies. That requires a fair amount of energy to input into the molecule to be able to break that bond. And so it's really then becomes more of like a chemical reaction because we're talking about a bond breaking in the molecule. And so that's something that we categorize as a transformation, a chemical transformation. And so then looking at these multiple bonds, they can't rotate. This really gives rise then to isomers, cis and trans isomers. And so because that rotation is restricted, it means that how we build or how we imagine or how it's synthesized or how it's found, how the molecule arranges its atoms around those central atoms that have a multiple bond, um, can't change without breaking bonds and reforming bonds. And so that's like a chemical reaction. And so here we have CH2Cl2, and we have a sigma bond between our two carbons. And then they're also connected by a pi bond, and it's a double bond right here. Well, because of that, where these chlorine are placed is pretty important. Especially remember, think about polarity. So like the placement here means we have a polar molecule, but if I put them opposite each other, like over here, it would not be a polar molecule. It would be nonpolar. Those would cancel out their dipole moments. And it can't switch between the two because it would require breaking that bond, that pi bond. And so that gives rise then, as I said, to cis and trans isomers. And we define those as having things either on the same side of that multiple bond or on opposite sides of the multiple bond. So the cis isomer has the chlorines on the same side of this carbon-carbon double bond. And that's what we call cis. And if you think about it, at least in this case, where chlorine is such a big atom relative to hydrogen, that's going to create a lot more negative repulsions from the electrons, the valence electrons on the chlorine atoms that might bump into each other, or they'll be closer together. Then looking at trans isomers, what we see is that things are on the opposites of sides of the double bond. And so it needs to be not necessarily two things that are the same, well, I guess so, but like something that's not a hydrogen. These chlorines could be carbons too, and we would still have a cis or trans isomer. And so here we've get this kind of zigzag where the chlorines are on opposite sides of the double bond. And so you can see there's a little bit more space for their electron clouds because they're now closer to a hydrogen rather than to another chlorine. So in this particular case, I would argue that the trans isomer would be a bit more stable. And so because of this, we get things like like trans fatty acids or cis fatty acids. And so you see these double bonds especially come up in these conjugated carbon-carbon chains that we see in biology a lot. So this would be all trans isomers, and they would have other stuff, bonded to these carbons. Whereas the cis isomer would be, so this will end up being a straight kind of chain. A cis isomer would have more kinks in it because we would have our carbon, something like this. It doesn't really. And so we get these different kind of large structures for these molecules that are pretty interesting, and they can't convert between each other without undergoing a chemical reaction where they break bonds.